Good morning, everyone. Welcome back to another day of DevOps. I'm going to start with a question. How many of you has ever run code on the JVM? I assume I'm going to see all hands, even though I can't see the people in the hall. So you have a bunch of languages running on the JVM, right? And IBM has had its own production JVM for many years, and it's called J9. And we've been working on open sourcing J9 for a while now, and we're pretty excited to have another JVM out in the open. So in this presentation, we will explore the inner workings of OpenJ9. Before we start, just be aware that the information presented here is our current plan, but it can change. So please read these disclaimers if you're planning to use this information for anything. Who am I? My name is Bjørn Vårdal. I work for IBM. I'm a J9 virtual machine developer. I've been there since 2013. Some of the more public projects I worked on are method handles, lambdas in Java 8. I implemented var handles in Java 9, and I'm actively involved in the Valhalla project for future Java releases. For the occasion, I've written a microservice. It's a random word generator, and it's a little bit complex maybe, but the basic idea is that it prints a random word, and I'm hoping that bananas is random enough. So let's do a little live demo here. So I compile my source, and I get a class file. I package it up with all its dependencies into an uber.jar, and when I run it, I get a random word. That's great because, you know, live demos are always very risky. The point here is that you have all written code like this. And Java developers tend to think of the JVM as a black box. But you are here in this room. You came to this talk. You want to know what's going on inside that box. So let's open it. These are just a few of the things that are going on when you run your Java application. And we will focus on a few of them and we're going to use OpenJ9 as a model to explain the behavior. So obviously, something has to launch the JVM. And the Java executable is one of those launchers. But the cool thing about launchers is that anyone can write one using the invocation API. And the JVM, or any JVM launcher, is going to do something like this, plus some argument processing, etc. So the first thing it does is that it creates a Java VM and a JNI environment. And the Java VM structure is the central context that binds together and connects the rest of the JVM data structures and functions together. And then the JNI environment is this JNI environment that we all know from JNI development. And in the context of J9, it's also the main JVM execution thread. So that's your main thread. And the structure definitions are fairly simple. Their main purpose is to provide the functions for this invocation API. So data structures are important, because data structures, and not the algorithms, are central to programming. Because I mentioned two key data structures on the previous slide. The Java VM structure and the JNI environment structure. And in this talk, I will keep coming back to the data structure, because if you understand those, then it's much easier to understand what's going on in the JVM and how everything fits together. And hopefully, as J9 goes open source, this will help you work with the code and understand the design principles in OpenJ9. So let's get back to the launcher here. We quickly covered creating a Java VM. And the next thing the launcher will do is to find the main class. And this is a class that you usually specify on the command line. And according to the JVM specifications, that class looks something like this. And if you have worked with any kind of bytecodes before, for example, if you used ASM, or if you have dumped bytecodes using Java P, you have seen something like this before. And coming back to data structures again, is this structure good for storing information about a class's capabilities and the attributes of that class? Sure, it's good enough, good as any. But more importantly, is this data structure good for execution, for JVM execution? And from our perspective, the answer is no. And let's get back to the launcher, and you'll see why we don't think this is a good data structure for execution. So we have found the main class. The next thing we want to do is find the main method. And if we go back to the class file structure again, the main method that we want to find is right here. So in the methods part of the class file. So to get to that, let's try to do that. First, we have to traverse some fixed size fields. That's easy enough. But then we hit the constant pool. And the constant pool is not only variable number of elements. Each element within the constant pool has a variable size. So you have to walk it from beginning to end to actually get to the next part. We have some more fixed size fields, some more variable ones, and eventually we get to the methods and we can go find our main method. Now imagine if that was a process you had to go through every time you wanted to find a method at runtime. So to improve on this process, we need to layer some kind of structure on top of the class file that will allow the interpreter and the rest of the runtime to operate efficiently on the data. So J9 actually has a strong background in Smalltalk. And leaning on that experience and the good experiences with putting data in ROM, we decided to split the class file into two parts. The ROM part, which has the read-only symbolic data, and the RAM part, which has the live representation. So the ROM class is the ROM representation of the class file, and we have some conversion process to go between them. And the first part of that process is to do the static verification. And the static verification is basically making sure that the class file is correctly structured. So you take the attributes, the constant pool, the bytecodes, and you ensure that all of those are valid. For example, you take every constant pool index that is mentioned and make sure that it is within the range of the constant pool. And if we can do that, that means we can construct a ROM class. And so we have this ROM class builder that takes care of restructuring the data from a class file into the optimized data structure. And I could talk more about that conversion algorithm, but as I mentioned before, it's better to look at the data structure than the algorithm. But before we look at the ROM class structure, I want to look at pointers. Because ROM classes use this use this neat trick that you might actually find useful in many other contexts. So in a typical application, a pointer is just this. It mentions the address of where the data is. And if you move that pointer, or if you move the data, then you have to change the value of the pointer. So what I didn't mention here is that if you think of all this as a single data structure and you move the whole data structure, then when you move it, you have to update the data structure. But when I've been talking about ROM classes, I really mean ROM, as in read-only. And that would then imply that we can't move our ROM classes after we created them because we don't modify them. And is that really important? Yes. I will show you how we solve that issue, and I will also show you why it is important to solve that issue. But first, let's get to the solution first. The solution is self-relative pointers. So we also call them SRPs. So instead of storing the address of the data, we store the offset from the pointer to that data. So it's easy enough to get back to the target address. You basically take the address and the value at that address, add them together, you get your target address. And then if you move your SRP, or if you move the data structure, the value stays the same because my address changed. So now I'm looking at a new address, but my value is still the same, which means the offset is, because it's storing the offset, so my target address is automatically updated. So let's now get to ROM classes. This is the definition of the ROM class structure, or at least the part that fits on my screen. And just like the class file, I want my ROM class to exist as a single blob of data. So a class file is a file. I want my ROM class to be the same way. But the problem is that there will always be variable size data. So you have the size of the constant pool. We have different numbers of bytecodes. You have different lengths of the UTF-8 strings. So there is some variable size data. And this is a C struct, so we can't really handle that within the structure itself. So we add it to the end. So we moved all this variable size data out of line to the end of the J9 ROM class structure so that we have a fixed size structure that's easier to work with. And earlier we tried to get to the method by walking through the whole structure. And does that mean, has that really changed? Because what it looks like here is that I have to look at my constant pool size, then look at the interface count to get to my ROM methods at the bottom there. But I'm using SRPs. So in my fixed size ROM class, I have fields that are relative pointers down. One of the second from the bottom there points to the ROM methods, so we can easily get directly from the fixed size structure down to the variable size structures. And in the end, I still just have symbolic data, just like the class file, but I have improved the data structure, which is what I wanted to do. It's still self-contained, it's still location independent because of the SRPs, but now it's easy to access the elements without traversing the whole file. And there are a couple of interesting side effects of this design. The first one is that because we put our bytecodes in ROM and we never change them, that means I can't do any kind of bytecode quickening at runtime. I can only do it in the limited context I have when I loaded the class and put it into ROM. But a nice side effect of that, again, is the fact that I now have a path back from ROM class directly back to class file. So if I want to do stuff like, if I want to do class redefinition, I have the path back. I can get the class file from the RAM class, do the redefinition, and recreate the class. And these ROM classes are not connected in any way. So if you have a class foo with a superclass bar, foo only knows the name of bar. It doesn't have a pointer to it, and bar might not even be loaded. And it's the RAM class that has that kind of pointers. So we have ROM that, from the RAM, we can create the RAM. And the RAM is the live representation, which holds the real pointers, the real object references at runtime. And again, there is a conversion process. Has some interesting parts to it, but again, if we look at the data structure, the answers to how to do that are just going to pop out. So RAM class describes how this class is represented in this instance of the JVM. When we loaded the ROM class, we got the exact same result every time, but when you create the RAM class, that's going to be different for each JVM. First of all, because all the pointers are going to be different, because you're in a different area of memory, but also because it suddenly starts depending on its context. So if you change something in the superclass, that's going to be reflected in the subclass. So this is the J9 class structure. And as you can see, we're using real pointers now, not SRPs. And all this data has been resolved. I can get to my superclasses. I can get to my super interfaces. It's no longer symbolic where I just had the name, like the way I had in the ROM classes. But like the ROM classes, the RAM classes also has variable-sized data that has been moved out to make the RAM class fixed size. Specifically, we moved the virtual method table directly after the J9 class, and basically, that means the virtual method table, the idea is that when you resolve a virtual method, it becomes an index into this table, and then you can use that index in this class or a subclass, and it might resolve to different methods in the end. But one really cool thing we did here actually was to put the JIT's vtable above it, or immediately before the J9 class. So that way, it's just as easy for us to get to a JITted method, so a compiled method, as it is to get to an interpreted method. Other things from the J9 class, it has a pointer to the RAM constant pool, and an index into the RAM and ROM constant pools are equivalent. It's just that the RAM constant pool at an index will hold the live data represented by the symbolic data at the same index in a ROM constant pool. And the J9 class also has pointers to J9 methods. So these are also the live representations. These J9 methods are not the same ones as the vtable, because in addition to the virtual methods, it has the private methods and the static methods. And also the vtable doesn't only have its own virtual methods, it will also have the virtual methods that it has inherited from superclasses. Okay, now think about this scenario. We have, on a machine, we have 3 JVMs running at the same time, running the same code. This could maybe be that you're running a service, multiple instances of a service. And in each of these, when the classes are loaded, we get these ROM classes. And then all of these get turned into different RAM classes per JVM. And a few things to note here. The conversion from class file to ROM class will take time. Like, of course, it's running code. Of course, it takes time. And it always produces the exact same ROM class for any given class. And because it's ROM, they will never change. So they're guaranteed to stay the same for every single JVM. And ROM classes are, because they use self-relative pointers, they are position independent. So that means that this entire section, red section here, they're all duplicates across the JVMs. So do we have a solution for that? Caching. Each of the JVMs can share the ROM classes in this shared classes cache. And basically, like any other cache, it means instead of creating it myself, before I do so, I go check the cache, is it already there? And now you can see why these self-relative pointers were important, because they are the ones that enable, or they are the ones that make the ROM classes position independent, and thus enable us to put them in a shared cache across JVMs. And there are a couple of reasons to do this. The first one is footprint improvement. We see up to a 20% improvement in footprint because we share them across the JVMs. And another thing we see is startup improvement, because we no longer have to spend time creating ROM classes. We can just pick them right out of the cache, and and we get a startup improvement from that. And there's one more application that is very interesting now, becoming more and more interesting, which is the effect this can have in the cloud. Because imagine you have a Docker container, and in that Docker container you have your app, and the app runs on the JVM runs with a bunch of RAM classes, and those RAM classes are based on ROM classes from a shared classes cache. Now, why would you have a shared classes cache in a single instance JVM? You're just going to spin this container, you're going to start your JVM, and then you're going to shut it down and throw everything away. Why would it be in a shared classes cache? Well, the thing is, if you can create it in a shared classes cache that exists in a data volume within the Docker image, then you can pre-initialize them. So the Docker image itself has a shared classes cache, so every container you spin from this image will have a completely initialized shared classes cache, and that drastically reduces the startup time of your Docker container and the app within that Docker container. Okay. Let's move back to that launcher. We did a find class call, and what did find class return? It returned a J class, and a J class is a JavaLang object that represents it's a JavaLang class object. And where does JavaLang class fit into this model that I've shown you of how J9 treats classes? So far I've been talking about ROM classes and RAM classes, and those are loaded by the J9 class loader, and all these structures are placed in native memory, as opposed to the heap, which is where the garbage collector lives, or what the garbage collector controls, I mean. So by keeping these structures off the Java heap, it means that the garbage collector will not affect them, so we can easily access them and modify them without worrying about them moving around. And the heap is where Java-lang objects live, so that includes the Java-lang class and the Java-lang class loader. And these objects have pointers to their native structures, and the native structures have pointers to the objects. So that way, when the launcher then, or if class returns the Java-lang class, we can immediately get to the RAM class, which will get us to the ROM class. And we use the split model for other core structures as well, such as threads and modules. OK, so I have loaded all of my classes, and everything is good. Was there something else the JVM was supposed to do? I guess we're supposed to run some bytecodes too, right? And we saw in the ROM and RAM class slides how the bytecodes were loaded into the runtime with the ROM class. So the next step is to run these bytecodes, and that's the last step in the launcher when my clicker works. Yeah, that's the last step in the launcher. So after we have created the core structures, we found the main class, we found the main method, now we can finally invoke that main method. And this triggers the bytecode interpreter. And the interpreter is basically a big C++ switch statement. We used to write this in, it used to be written in Smalltalk, but this was quite a big barrier to entry for new developers to work on this code, and it was hard to get work done in this really important part of the VM. So in Java 7.1, we replaced that with this C++ code, and this came with a slight performance improvement, performance hit. When we moved to C++, but then we were able to recover that through some other performance improvement. And in Java 9, we have completely removed the last pieces of the Smalltalk code, so now it's a pure C++ interpreter. So this big switch statement, it executes bytecodes like the Java bytecodes, the A-load, A-store, get field, all the ones we know from there, and also what we call INLs. So those are Java native methods that we have linked directly into the interpreter. So for example, a method like object.getClass, in terms of overhead, is equivalent to invoking any bytecode. So in addition to this, the interpreter is also responsible for maintaining the Java stack and also doing transitions to the JIT, so the compiled code. So I mentioned earlier that the J9 environment structure is actually our main JVM execution thread. And these threads are what we call the J9 VM threads. And they are represented by a Java-lang thread in the Java heap. So this is still the red line there is still the separation between native memory and the Java heap. And on the below, it's represented by, or is backed by, an OMR thread, which is the platform abstracted native thread. So it will look the same on every platform that we run on. And each J9 VM thread is part of a unique instance of the bytecode interpreter. So it maintains the state to describe the execution on that thread. So it has some registers, if you like. So from the J9 thread, J9 VM thread, we can get to the J9 method, so we can get to the ROM method. So that's the current method that we're running. So we can get to the ROM method, and the ROM method has our bytecodes. And then the thread's PC register can point to the bytecode index where we are currently executing. And then on the side of that, we have the Java stack. And the basic structure of the Java stack is that we have, for any method we're executing, we have the method arguments to that method. Then we have the current, the local variables. And then there's a method frame, and on top of that, we have the pending pushes. And then back to the VM thread, A0, so another register, can then points to the 0th argument, which allows us to quickly get to our argument, and it also saves the base pointer register, because we don't really need that anymore, because we know how many arguments we have, so we can get to the frame easily. And then we have the stack pointer, which points to the top of the stack, or bottom really, the lowest live value on the stack, basically. And most of the time during execution, all of these registers are really live, as in they are actually in the machine registers. Because we operate in a cooperative threading model, we don't actually have to write these registers back into the fields in the J9 VM thread unless we're going to release our VM access, which is what we do when a GC might occur. And then when we come back from a GC, we can just, and we reacquire VM access, we can pull those fields back out of the J9 VM thread, throw them right back into the machine registers, and keep running. So in terms of registers, it's as fast as native. So we obviously need to be able to run multiple threads for multi-threading, but also because GC threads and JIT threads also are J9 VM threads. And each of these threads are completely self-contained. They don't rely on any statics, which makes it easy to have multiple threads at the same time. So the J9 Java VM, which is the Java VM structure we looked at earlier, it keeps a circular linked list of all these J9 VM threads, and this makes it easy to walk all of them, so that when we need to tell all these threads, like, get ready for garbage collection, it's easy to walk through all of them and make sure that we're ready for that. And each of these threads has an interpreter state that we saw earlier, and they also all have a Java stack that we saw earlier. So that brings us to the end of the JVM execution. Before we move on, I want to summarize what we've seen so far. In terms of the launcher, we saw create Java VM, which created the Java VM in the J9 environment, which is our main execution thread. And then we ran find class, which found the class and loaded it in as a ROM class and then to a RAM class. And then there was get static method ID, which found the main method within that main class. And then we used call static void method to call that main method, which was executed by the interpreter. But that's only half of it in terms of executing a method, because we don't run everything interpreted all the time. There's the JIT, right? So I mentioned the JIT compiler a few times already, but the JIT is quite a bit more than just a compiler. So let's take a closer look at what is in the J9 JIT compiler. From a fairly high-level perspective, there's the profiler, and the profiler is used to determine what code is important to us. What code do we run all the time? What are the paths always taken, the paths never taken? And do we have situations where, for example, we're invoking a method on an interface, but we actually found that we only ever loaded one implementation of that interface, so maybe we can just use that implementation always instead of going through the roundabout way of doing an interface. Then there's the runtime configuration, which is where we get configuration information like, do we know something about this type of runtime? For example, the JVM or Java specifically. What resources are available and what options were given to us by the user. For example, did they tell us to use a specific compilation level? Then there's the IL generator that, well, generates IL. So it takes the bytecodes and turns them into an intermediate language that we can then feed to the optimizer. And the optimizer will optimize based on information it gets from the runtime environment and the profiler. And based on that, decide what code to optimize and how much to optimize it. And it will then hand that optimized code over to the code generator, which is then platform specific, so it will generate machine code for the platform you are on, and then hand that code back to the runtime for execution, along with some metadata, because some of the assumptions that I mentioned in that maybe the profiler made that, oh, we only ever have one implementation of this interface, or we always take this path, those could be invalidated later on when we suddenly find that, well, they're no longer the case. So then we use that, we have that metadata available so that we can backtrack on those assumptions. So I mentioned that the optimizer could decide how much to optimize the code. And this is possible because we have this tiered compiler that transitions methods through different levels of hotness. And the basic idea there is that you shouldn't spend more time compiling the code than the total time that you would run it, right? It doesn't make sense to take code that was going to run for a total of 3 seconds in the lifetime of the JVM and then spend 5 seconds compiling it to make it fast. So the first level of hotness, which is called interpreted, freezing, there's no JIT involvement other than profiling, trying to figure out if we should compile it. And then the next level, when we have some data about how much we use this, we might decide to compile it, and then early on we might say, compile this to cold, which is fast but doesn't create very fast code. And then later on we might find that we have a bit more information, we use this method quite a bit more, so we compile it to warm, which takes a little bit longer to compile, and but then also gives a little bit faster code. And then after that, we keep sampling to try to figure out which methods should make it to the next level, the hot level. And when we find those methods, we can keep running the code we already have available, compile hot level in the background, and once it's ready, we replace the method we have, and we can the method in the runtime, and we can then start running at more optimized code. So after hot, there's also the scorching level, but in between them, there's this profiling level. And the idea there is that to get to scorching, we need a lot of profiling information. So instead of sampling from the side and trying to figure out what this thing is doing, we actually take the hot code and we drop profiling points inside the method. So that way, we get a lot more profiling information every time this method runs. We get perfect profiling information, and we can create this scorching method, which is blazingly fast. If we go back to that shared classes cache that we looked at earlier, so once we had a cache, we thought, what else can we put in there? And the obvious answer to that is JITted code, because we found that most applications actually run the exact same code every time they're executed. So we created this dynamic AOT, meaning that the code is compiled ahead of time, but it's done dynamically by the JIT at runtime. So the first time they're not there, but then we do JIT compilation, and then that becomes the ahead of time for the next invocation. So we started resulting JIT code in the shared classes cache so that the next time the JVM starts up, it can spend less time compiling the code and more time running it. And this has a startup improvement of maybe 10 to 30%. I started off by talking about going open source, and that's the important thing here. So how can you play with this code? If you're interested in getting access to the code, a lot of it is already out there. When we started our move towards open source, we started by taking the core of the JVM, the language-independent parts, and we open sourced that in the Eclipse OMR project. And this makes it possible, the Eclipse OMR project makes it possible for other runtimes, such as Ruby, Swift, etc., to reuse language-agnostic components, for example, like a platform abstraction layer that I mentioned earlier, or the garbage collector or the JIT, and you can reuse those in their own runtime. And J9 also uses the open source class libraries from OpenJDK. So, in fact, J9 is really a distribution of OpenJDK where we took out the hotspot VM and we put in the J9 VM. So most of the code is already open, and the core of J9 is the one that's coming soon. And like any company, we'll continue to have the IBM Java SDK, which we will build directly from OpenJ9, plus some small IBMisms added on. But our intention, and this is important, our intention is to develop in the open, and so that changes go in to the upstream projects first. So the upstream projects being OpenJ9, OMR, OpenJDK. I mentioned the Eclipse OMR project, and that was the first step on our journey. The Eclipse OMR mission is to create an open and reusable language runtime foundation. And the idea behind that is that if you share the foundation, then improvements in that foundation is going to have a wider benefit. So if we improve the JIT compilation or the garbage collection or something in J9, that can immediately become better JIT compilation, better garbage collection in Ruby, Python, etc. Eclipse OMR aims to work with the language community that already exists. There's no benefit to splitting off on the side. So OMR, the OMR people, or us, we work with professionals, we work with hobbyists, we work with researchers, everyone out there, to create a better runtime using OMR. And you can get Eclipse OMR source code from GitHub, and the other links here will also give you more information about that project. I want to point out the license, though, because Eclipse and Apache public license, those are very permissive licenses, and that's really to your benefit. And a few of the OMR components. We have that platform abstraction library that I mentioned a few times that allows you to write code to the abstraction layer so that you can easily port your code across platforms without having to if-def in every platform difference. And then we have the thread library, which is really an extension of the port library. So it's platform-independent threading support. And then there's the garbage collector, which is the full force of our garbage collector. And you have the JIT builder, which is a very easy way of getting a JIT into your runtime. So there are many runtimes out there at the moment that they maybe have a garbage collector, they have different things, but a JIT is something that is not that easy to get going on. And with OMR, you can get a JIT builder going, and you have JIT in your runtime. So what we have here is anything from the port library to a test framework that will help you either improve an existing runtime or just build a new runtime. So more components are coming, so go check that project out. So why are we doing this? To quote IBM's president, CEO, etc., we believe that open ecosystems and partnership are key to future innovation. Didn't help that much, so really, why are we doing this? Well, the first point is collaboration. Because we want to work with the community, we want to be able to, when we are trying out a new feature, to give it to people. We want to be able to have people come with ideas to us, but that is really hard if the community can't see the code, if our partners, our customers can't see the code. So we want to make it easier for everyone to work together on this code, and the keywords are rapid innovation, which collaboration will enable. One JVM is good. There's a big one out there, but multiple JVMs is better. Competition makes runtimes better. Competition has made runtimes better for many years. This is why Java is fast now, is because we have constantly been competing on that performance at the same time as we have been collaborating on the specifications for the JVM. So having two major JVMs out in the open will enable the community to participate in this competition. In IBM runtimes, when we enable some new feature, for example, RDMA, we immediately get the question, so when is JavaScript, Swift, Go, Ruby, Python, when are they all going to have this feature? And by sharing the foundation through OMR, it's easier to bring the features to new runtimes. So that's one thing. And the other thing is that open source makes it easier to enable interop between the runtimes. So in the polyglot world, that is going to be very important to enable this through the open source. And there's also the platform point. Being open makes it easier to move to new platforms faster. So where we maybe didn't have the focus or wouldn't focus on a particular platform, putting the code out in the open means that anyone in the community can pick it up and port it to a new platform where they want it to run. And that will immediately benefit the rest of the community. We already support multiple platforms, which means that we have kept the implementation honest about itself, so it doesn't make any assumptions about the platform. And that makes it easier, again, to move it to new platforms. And that doesn't just apply to CPU architecture and OS. It's also about other pieces of the hardware like GPUs. So the two words that summarize why we're doing this are rapid innovation. And talking about rapid, when is OpenJ9 actually going to come? And the answer is soon. We are working on this in parallel with implementing Java 9 and all the other things we have going on. But the goal was to have it out with Java 9. Java 9 schedule has shifted a bit, so that might mean that OpenJ9 is going to come out a little bit earlier than Java 9. So thank you for listening. I hope you are as excited as me about getting another JVM out in the open. And when it's out there, go out, clone it, and get started on hacking away at it. Thank you.